Hello everyone, I am Himanshu Vasnani from Department of Mechanical Engineering. I am here to give you a lecture on the subject Material Science, subject code ME207, unit number 3, lecture number 16 in the series, and today's topic are quenching medium and tempering process. So, today's learning objective are to provide the student with a basic understanding of quenching medium and tempering process. And today's learning outcome will be the student have learned the basics of quenching medium and tempering process, and students have understood various steps of tempering process. So, the influence of quenching medium, specimen size and geometry. Okay, now earlier discussions we have discussed about the influence of both alloy and alloy compositions and cooling or quenching rate on the hardness. Okay, when we are studying about hardenability and hardness, we discussed everything about it. So from that we say that the cooling rate of a specimen depends on the rate of heat energy extraction, which is a fraction of the characteristics of the quenching medium in contact with the specimen surface, and also on the size and geometry of the specimen. Okay, the cooling rate, the you can say when you heat a material and then you try to cool it down in a medium. Okay, the medium may be water, the medium may be oil or some salt solution. Okay, then whatever you are try to cooling, that the cooling rate of the specimen, it depends on the rate of heat energy extraction. Okay, and that heat energy extraction is a function of the characteristics of the quenching medium in contact with the specimen surface. The medium which you are using for cooling, for quenching, okay, it depends upon the characteristics. It is in contact with the specimen surface and also on the size and geometry of the specimen. Okay, if it is bigger, then it will take different time. If it is smaller, then it will take different time. If the geometry is complex, then also the parameters are changed. If the geometry is simpler, then also the thing. So, severity of a quench is widely used to express the rate of cooling. Okay, the rate of cooling is expressed with severity of quench. So, interestingly, the more rapid the quench, the more severe the quench. Okay, the more rapid the quench, the more severe the quench. Water, oil, and air are the three most common quenching media that we are using in today's world. Okay, somewhere some salt solutions are also used depending upon the applications. Okay, and out of these three, the water produces the most severe quench, followed by oil, which is more effective than air. Okay, out of these three, water, oil, and air, water produces the most severe quench. Okay, the more rapid the quench, the more severe the quench. That is the line. That is the thing. So water produces the more severe quench, followed by the oil, and which is more effective than air. So the degree of agitation of each medium, okay, also influences the rate of heat removal. Okay. Now the influence of quenching medium. Okay, then the quenching effectiveness can be enhanced by increasing the velocity of the quenching medium across the specimen. Okay, you can see in that diagram on the right hand side, they have taken, you can say, the work pieces. Okay, and now they are trying to quench them in a water solution, or you can say in a water quenching medium, and then they are trying to cool it down. So you can see that as soon as the work pieces come in contact with the quenching medium, a lot of heat is dissipated. It is released before because the workpiece that is getting you can say dipped in the you can say quenching medium, it is trying to cool it down, and at very that moment the heat is being released by the workpiece. Okay, so the quenching effectiveness, okay, that can be enhanced by increasing the velocity of the quenching medium across the specimen. Okay, here it is dipping, but somehow if you want, you can also try to you can say flow the workpiece. and if you can increase the velocity, then more amount of heat can be released easily by the workpieces. So oil quenches are found suitable for heat treating of many alloy steels. Okay, for alloy steels, oil quenches are commonly used. A water can quench is too severe. Okay, now carbon steels, well, because the water quench is too severe for high carbon steel because cracking and wrapping may be produced. Okay, so for them, the cracks may appear. Air cooling of austenized plain carbon steels ordinarily produces an almost totally pearlite structure. Okay, so normally in a austenizing process, you can say for you can listen, have obviously listen about annealing process. So in annealing, normally we go, you can say cool down the workpiece in the furnace only. Okay, and a normalizing air quenching process is commonly used because what you do, you take out the workpiece after normalize after heating to a particular temperature, then you keep the workpiece in open air, and the obviously the cooling rate is faster in normalizing than annealing. So air quenching takes place in normalizing process. So we can say that air cooling of austenized glazed carbon steels ordinarily really produces an almost total polytic structure, which is during the quenching of a steel specimen, heat energy must be transported to the surface before it can be dissipated into the quenching medium. Okay, as a consequence, the cooling rate within and throughout the interior of a steel structure varies with position and depends on the geometry and size. Okay, it depends upon the geometry and size because the cooling rate that you can say that the rate at which the cooling is taking place of the workpiece, okay, within and throughout the interior of the steel structure. Now we're talking internally about it. Now it depends upon the geometry and the size also. Okay, if the size is bigger, it will take more time. Okay, and geometry is also is an important parameter in this. You can see in the diagram on the right hand side how this workpieces are being dipped inside the quenching medium and then allowed to cool. Okay. Now different industries have different quenching mediums and the process of cooling it. Okay. So it depends. I have shown you in the figure in the previous figure also. It was, you can say, the whole workpiece was taken together and then dipped into the quenching medium. Here the individual workpieces are there because here the size is big. Okay, so here they have to dip it individually, but in the previous the size was smaller. So there they took a lot of in one lot and then they tried to dip it into the quenching medium. So it depends upon the application in the at the geometry and size of the workpiece also. The heat energy is dissipated to the quenching medium at the specimen surface. Okay, and the rate of cooling for a particular quenching medium. Okay, to quenching treatment, sorry, for a particular quenching treatment depends on the ratio of the surface to the mass of the specimen. Okay, the larger this ratio, look, ratio of surface to the mass of the specimen, surface to the mass of the specimen. The larger this ratio, the more rapid with the cooling rate. The larger the ratio of surface to the mass of the specimen, the more rapid will be the cooling rate. I repeat, the larger the ratio of surface to the mass of the specimen, the more rapid will be the cooling rate. Okay, and consequently, the deeper the hardening effect. Okay, now irregular shapes with edges and corners have larger surface to mass ratio than regular and rounded shapes, and thus are more amenable for to hardening by quenching. Okay. Now there are a multitude of steels that are responsive to Martens's heat treatment, and one of the most important criteria in the selection process is hardenability. We have studied about hardenability in our previous lecture. So hardening may cause few defects. Okay, somehow they call make cause some defects due to prolonged or uneven heating, temperature higher than required, improper cooling. See, these are some, you can say, parameters on which the defects may cause. Okay, defects may happen. So hardening may cause few defects due to prolonged or uneven heating, temperature higher than heating and improper cooling. So we have to be careful. Like some defects they have discussed. Here also you can see the in the right hand side how they are trying to do quenching process. Okay, the workpiece is so larger in size, so it is carefully put it inside the quenching medium. Now the defects, few of the defects are like hard and soft spots. Okay, the hard and soft spots due to the uneven and prolonged heating. Now you can see in the diagram also I have shown the quenching. Okay, here the parts are a little bit smaller and now the bigger parts are here in the image. So it will give you a better idea of quenching. Now defects, we are studying about defects. Sorry. Now we a few of the defects are hard and soft spots due to uneven and prolonged heating. Okay, hard and soft spots on the surface. Okay, due to uneven and prolonged heating. Okay, excess heating will also lead to that. Okay, those defects this is a kind of a defect. Okay, a few of the defects mean oxidation and decarbonization due to high temperature. Okay, now mechanical properties achieved different from anticipated what they have planned, they have achieved different properties. Now, wrappage due to higher temperature, obviously. Now, change in dimension due to heating or cooling. Some dimensions may change due to somehow shrinkage effect may come, so size will become lesser. Okay, or may sometimes cracks may appear, so it may lead to some issues. Then cracks, okay, the cracks either of circular or vertical nature due to uneven heating. So these are some kind of defects that have. Now the tempering process. Okay, we had studied till now about the tempering, sorry, heat treatment processes of like annealing, like normalizing, like hardening. So after that, tempering is also a kind of you can say a heat treatment process. Okay, that is normally applied to alloys. Okay, alloys. You can say to make a better, you can say better metal structure, or you can say to improve the properties of the workpiece for a certain application. Okay, so obviously heating at multiple temperatures may occur in this also. Okay, this is a diagram in the right hand side. You can see how the heating takes place. Okay, they don't melt it; they just heat the workpiece to a particular temperature and then they go for the further processes. So, tempering and aging are the kinds of a heat treatment which are applied to hardened alloys. Okay, now they involve certain phase transformations which make the metal structure approach the equilibrium. Okay, now a combination of hardening and tempering or hardening and aging. I repeat, a combination of hardening and tempering or hardening and aging is almost always aimed at obtaining higher properties like hardness, strength properties, coercive force, electric resistance, etc. as compared to those resultant from annealing. Okay, they say that either you go with hardening and tempering or hardening and aging. The purpose is that they after this process they go for the properties that achieve are hardness or coercive or electric resistance, etc. as compared to those resulting from annealing after annealing. So they have a difference of properties. Now in most alloys, hardening forms a super saturated solid solution or a mixture of solid solution. In that case, the main process occurring in the subsequent tempering or aging is the decomposition of the supersaturated solid solution. The temperature and the holding time are chosen so as to avoid the formation of the equilibrium state in the alloy, as in the case of annealing. Okay, because when you are heating a particular workpiece to a particular temperature, then also they have a holding time. Why? Because so that you can say the proper work, the stresses may be easily relieved. Okay, now the rate of cooling after releasing stresses, then the rate of cooling from the temperature of tempering or aging has no effect on the structure and properties of alloy. Okay, the rate of cooling from the temperature of tempering. the temperature of tempering or cooling. Okay, because we had heated the workpiece to a particular temperature and hold it there. Now the rate of cooling, now we are trying to cool that. The rate of cooling from the temperature of tempering or aging has no effect on the structure and properties of alloys. Okay. So the term tempering is usually applied to steels and other alloys undergoing a polymorphic transformation in hardening, like two-phase aluminum or bronzes or some titanium alloys, and the term aging to alloys which undergo no polyformic transformations in hardening, like some aluminum alloys or austenitic steels, nickel alloys, etc. So here is the you can say the thing. Now tempering releases the stress and reduces the bitterness. See, either you go with the normalizing process or you go with the other processes. They try to release the internal stresses, okay, caused due to any kind of processes, any kind of making processes, like okay, and then in tempering, what they do, they release the stress and reduces the bitterness also. Okay. Then tempering causes the transformation of the martensite into less brittle structure. Okay. That is a fine pearlistic structure termed as trustite. We have studied about trustite structure in the iron carbon diagram. Okay. It is a kind of a fine pearlistic structure, kind of a shining structure. Okay. But it has less brittleness. Okay. It has a less brittleness. So trustite is much tougher, although somewhat softer than martensite. Okay. Now most cutting tools have this type of structure. Now once the tempering temperature has been reached, it is normal to quench the steel. Okay. So all the structures resulting from tempering are termed as tempered martensite. You can name these structures from like this, a tempered martensite. Okay. Now you can see in the diagram on the right hand side how there are big you can say workpieces that are heated to a particular temperature and uh, lead to some kind of heat treatment process. Okay. So now changes that take place during the various temperature changes are as follows. Like the first, they go for 100 degree to 220 degree centigrade. Excuse me. Right. Now the first one is 100 degree centigrade to 20 degrees centigrade. Below, this says that below 200 degrees centigrade, tempering temperature only relieves the hardening stresses and very little change occurs in the microstructure. However, the stress relieving treatment is given when maximum hardness is desirable and the brittleness is a problem. The strain is relieved due to the removal of carbon atoms from their trapped positions. Okay, the strain is relieved in this. Okay, because the carbon atoms, okay, they move from the trapped position, so the strain is relieved from the material. Okay. uh then the second stage is the 240 degree centigrade to 400 degree centigrade. Now above 220 degree centigrade, the martensite, this starts to change into a fine pearlitic structure termed as fusite. We have discussed about the structure in the previous slide also. Okay. Now in the range of temperature 240 degree to 400 degree centigrade, martensite decomposes rapidly into emulsified form of pearlite called as secondary fluorite. Okay, emulsified form of pearlite. Okay, it is called as secondary fluorite. Now, as the name said, secondary fluorite. Okay, now this type of material is very fine in nature and hence provides a good shock resistance. Okay, the fine edge tools are usually tempered within this range, that is 270 degree to 300 degree centigrade. Okay, now you can see in the diagram also how this sheet is rolled. Okay, now 400 degrees centigrade to 550 degrees centigrade. Now tempering above 400 degrees centigrade causes the cementite particles to ball up, giving a core structure called a sorbite, which is more ductile and tougher than true site. Okay, now they are going with another structure that is named as sorbite. Okay, it is more core structure than you can say fused. Now, within this range, the precipitate fused begins to coalesce, forming a coarser form of globular pearlite called as sorbite. Okay. Now, both fused and sorbite, okay, now are specifically called as tempered martensite. Okay, we have discussed about this term previously also, that after tempering the materials normally are called as tempered martensite. The treated is usually preferred in such components as beams, springs, and axles. Now 600 degrees centigrade to 700 degrees centigrade. Now within this range, heating hardened steel causes spheroidization, the structure being known as spheroid. Now this structure is formed due to the further coalescence of the carbide within the alloy. Now spheroidized steel exhibit fairly good machinability as the hard carbide particles are embedded in the soft ferrite, okay, matrix, and consequently do not have to be cut by the cutting tool. Now this is somewhere really good because now materials at this temperature they have the good machinability. Okay, because the hard carbide particles these are emitted with the soft ferrite matrix. Now when the spheroidized steel is heated to just above its lower critical temperature, the pearlite present, okay, the pearlite present will alter to austenite, okay, and then cooling to room temperature will yield a structure of laminar pearlite, thus plus proeutectoid ferrite or cementite depending upon the carbon content. Now here the carbon content plays its role because when you heat the spheroidized steel just above its lower critical temperature, then again the pearlite that was present, it will change to austenite, and then when at that point you start cooling the workpiece to the room temperature, it will yield a structure of lamellar pearlite or you can say plus prototype ferrite, but it depends upon the carbon content. Okay. Now, usually the temperature of tempering is judged by color appearance on shop floors. So, however, for accuracy, the exact temperature measurement are to be made. Now, I will show you some tempering temperatures and the color appearance for various tools. Like we can say that for planning tools, the temperature is around 200 degrees centigrade, and normally the color is pale yellow. For drills and for milling cutters, the temperature is around 240 degrees centigrade. Okay, the tempering temperature, and the color maybe is dark straw. Okay, then for taps and screw cutting dies, we have 250 degrees centigrade, and the color is normally brown. For punches and drill bits, the color temperature is 260 degrees centigrade, the color is purplish brown. For press tools, we have this temperature for cold chisels, for wood saws, springs, okay, and turning tools. We have the different temperatures for this. 300 degrees centigrade, turning tools 245 degrees centigrade, then light lathe tools 30 degrees centigrade, razors 235 degrees centigrade, twist drills 270 degrees centigrade, boring cutters, reamers, we got depth 245 degrees centigrade. So they have their own structure. Okay. Now also some some kind of surgical instruments. Okay, they also have their temperature like 220 for 25 degrees centigrade, and the color is light yellow. So somehow there are also other you can say examples which say that they have different color. Okay, now I'll show you the image having some colors. Like you can see in this also the tempering color of steels. So here the different colors are also displayed. Okay, somewhat like brown, somewhat like dark blue. Okay, so here you can see that different temperatures like 176 degrees centigrade, 204 degrees centigrade, at 500 degrees and the 260 degrees centigrade, how the brown colors came. Okay, so different colors are there at different tempering temperatures. Okay, here also you can see it. With the effect of tempering on mechanical properties. Now this is somewhat really important. Okay, Uh, the tempering it improves the ductility and toughness of a quenched steel. while decreasing hardness. Okay. Now, the this you can I'll show you the figure that shows how these properties are affected by tempering. But before that, let me read it. The tempering temperature is so choosing that it results in the decreased in the desired combination of properties. Okay, the tempering temperature is so chosen that it results in the desired combination of the properties. There are some steels which exhibit drop in impact values in the certain tempering temperature range. And this drop is an indication of brittleness and one should avoid such changes. Okay, for mild steel, this brittleness, termed as blue brittleness, occurs at about 300 degrees centigrade tempering temperature. So, based upon the past data, they have this tempering temperature that for a mild steel, the blue brittleness may occur at 300 degrees centigrade. Okay. Now, this you can say is kind of an example available with you that what effect of tempering has does it on you can say has on mechanical properties. Okay. Now let me show you this figure 10.9. You can see that on the horizontal axis you have the tempering temperature in degree centigrade. On the horizontal this axis you have tempering temperature in degree centigrade. And on the vertical axis you have the stress or the ductility percentage. Okay, so they have their respective values in it. You can see that's how this hardness is getting, you can say, reduced, and how the elongation is getting increased at after a certain temperatures. Okay, so you can see that you can see with the arrow denoting B and HN, the arrows here, and how it is getting decreased. Then the elongation is also is happening there, that it is getting increased after a particular temperatures. Okay, then also you can see the reduction of area also is there. It is you can say it's increasing after a particular that there's a temperature increasing, then also it is also increasing. Okay, so this property chart of the or tempering diagram for water quench. Okay, then they have taken a sample of 28 diameter of bars of EN12 steel. Okay, now the application of a particular kind of a heat treatment, okay, it can be determined in principle by means of phase diagram. So in that connection, it is possible to distinguish the following main groups of alloys. That is, alloys which undergo no phase transformation in the solid state, alloys with a variable solubility. Okay, alloys with a variable solubility of the constituents in the solid state, and third the alloys undergoing electrolyte transformation. So how they have distinguished, okay, the main groups. Now tempering bath. Okay, now you can say after discussing with how at different temperatures the tempering process is done and how the color formation also tells us the different temperatures. Now the tempering bath. Now, mainly following three types of tempering bath are used for tempering of steel parts and cutting tools. The first is lead bath. Now, lead or lead alloy bath may be used for tempering steel parts. The parts are preheated. Okay, they may be used for tempering steel parts. Okay, the parts are preheated and then immersed in the bath, which is already heated to a tempering temperature. Okay, now once the parts they reach the tempering temperature, they are taken out and cooled to attain the required temperature. Okay, so lead bath has its own style of cooling. Okay, now salt bath. Salt bath, salt baths carrying liquid nitrates or nitrates plus nitrites are used for higher temperature. Okay, the salt used for these baths are generally chlorides and fluorides. These baths are very widely used for tempering of high speed steels. Okay, high speed steels they go for the salt bath. Okay, so they can be used for temperature range up to 540 degree to 600 degrees centigrade. From efficiency economy points of view, salt bath cannot be used below 170 degrees centigrade. So they have its condition that it cannot be used below 170 degrees centigrade. Now, oil bath. Oil bath is also important, so let's discuss about it. Oil baths can be employed for various temperature ranges. Okay, like for example, mineral oils are commonly used for these baths. Light oil baths are used for temperatures up to 230 degrees centigrade only. Okay. Now, heavy oil bath can be used for heating range from 343 degrees centigrade to 370 degrees centigrade. For oil heating the bath structure, bath temperature, for oil heating the bath temperature is first raised to the required tempering range and then partially heated component is immersed in it. So if the temperature of the bath falls below the required level, both the bath and the immersed component can be heated together to the tempering temperature. Okay, and the component has reached the required temperature. It is removed and immersed in the tank of caustic soda, followed by quenching in hot water bath. So this oil bath has its own style of processing. Okay, it has a range that it can be used for heating range from 343 degree to 370 degrees centigrade. Okay, and we can say the bar temperature is for raised for required to the required temperature and then partially heat component is immersed in it. So it has its own methodology of getting you can say giving this tempering oil bath in this. Okay, now the next. Now special treatments are there for you can say other processes. Now we study about special treatment. In case of large sections where the water quenching may produce cracks. Okay, water quenching may produce some cracks. Special treatments are preferred for hardening. Now the cracks on the surface are caused due to fast skin cooling. Okay, the upper layer, the surface. Okay, now the cracks on the surface are caused due to fast skin cooling and changes into martensite while the inner core cools slowly and transforms later accompanied by dilation. This dilation causes outer skin to crack. Okay, in order to avoid this type of cracking, special treatments have been developed. Since we are cooling and due to the fast cooling of the outer skin, cracks can be developed. है ना? So we can avoid this type of cracking by using some special treatments. Okay. So it would be proper to have some idea about some isothermal transformation. It will give you a better, you can say, overview. Now, isothermal transformation. This is also very important kind of topic. And usually, austenite is not converted into martensite instantly, but the process continues for some time. Okay. It is observed that different steels take different time for full transformation, and the time depends upon the temperature from where the cooling has begun. Okay, see, different steels have different compositions. Okay, so they take different time for full transformations, and so the time depends upon the temperature. Okay, from the temperature from where the cooling has begun. So conditions of constant temperature are termed as isothermal. Okay, the related phase diagram, that is, the related phase diagram are referred to as isothermal transformation diagrams or sometimes as triple T, time temperature transformation diagrams. Okay, we have studied about this triple T diagram also in the previous lectures where they say that they do it for a particular materials. The selected specimen is austenized and then quenched in liquid bath held at temperature to be investigated. So the specimen is held for a different length of time in the bath and then quenched in the water. Okay, the specimen is held there for a different length of time in the bath only and then quenched in the water. So the resulting structure that we have obtained after this can be studied under microscope or any other associated property. For example, this hardness can be studied or whatever test you can do. You can do it and then check the hardness also. So it is observed that definite times are required for the initiation and completion of the transformation. Okay, depending upon the composition, there is a different you can say a definite time is required for the initiation and completion of the transformation. And these times vary with the temperature also. Okay, so the progress of transformation, say for 10% or 50% or 90%, may also be determined. So this figure that we have discussed, that which I showed just now, illustrates complete transformation diagram for retectoid steels. Okay, you can see this diagram. Okay, this is a diagram of isothermal transformation diagram for retectoid steel. Okay, so structure present after 10 to the 5 seconds are shown on the right hand side. So you can see in the horizontal axis at the bottom. Okay, there is a time in seconds. So it has like 1 and 10 seconds, and 10 is to power 2, then 10 is to power 3, then is to power 4, 10 is to power 5 seconds. Okay, so the structures are present after 10 is to power seconds. Seconds are shown to on the right hand side. Okay, as it is in the bottom, so you can understand. So on the vertical axis, okay, on the left hand side, you can see the transformation temperature is there, like 100 degrees centigrade, 200 degrees, 300 degrees, 400 degrees, 500 degrees, 600, 700 degrees centigrade is there. And you can see there's kind of a curves going on at like start of transformation and then 50% transformation and then finish of transformation. These curves are having a particular shape. Okay, and on the right hand side, you can see that the different microstructure technical names are written like at this range of temperature. Okay, and then after this time, after this much time period, you can get some martensite or you can say martensite and bainite structure. Okay, and on upper, if you go upper, then as you increase the temperature of particular time, then you will get lower bainite, then upper bainite, then fine pearlite, then coarse pearlite, then austenite, and after a particular temperature, austenite you will get. So different microstructures are formed in this diagram, that is the isothermal transformation diagram. So let's study about it. The transformation temperature is lowered from A1 temperature to about 550 degrees centigrade. Okay, they have shown you there. And the nucleation and the completion time decreases and the pearlite level becomes finer. The nucleation and the completion time increases from about 550 degrees centigrade to 250 degrees centigrade, and the transformation product is bainite. Okay, it's composed of two equilibrium phases, that is ferrite and cement type. So minimum nucleation time is identified as the nose or the knee. You can see at the this bottom a kind of a nose is that is formed in front of bainite. So it's called as a nose or a knee in this diagram. Okay, you can easily see with that. The transformation product is also martensite below about 2 degrees centigrade. So although it forms almost instantly, okay, this forms almost instantaneously. But the amount formed depend upon the temperature. The upper and lower limits of martensite formation temperature are represented by MS and MF respectively. So these diagrams are also referred to as S curve because of their shape. Okay, so these diagrams are referred to as S curve because of their shape. Okay, so that's matter. Do we have some time? Yeah, and I'll start with the MCQ now, because MCQ is important in this. Ah, so MCQ. The cooling rate of a specimen depends on the rate of heat energy extraction, which is a function of the characteristics of the quenching medium in contact with the specimen's surface and also on the size and geometry of the specimen. Okay, we have discussed this in the quenching medium. Okay, and it is asking that it is giving a statement that the cooling rate. Okay, it depends also on the size and geometry of the specimen. Okay, bigger the geometry, okay, the more time it will take for cooling down on this, and the more the size also it will take more time. So obviously depends. Secondly, it is also the function of the characteristics of the quenching medium also, which is in contact with the specimen. So both factors of obviously are in consideration. So if we take both factors as an important consideration, so this statement is true. Okay. Now, severity of quench. You can say it is widely used to express the rate of cooling. Obviously, we have discussed in the starting only about this term, severity of quench. The more rapid the quench, the more severe the quench. Okay, and out of this, we have studied about that water, I think, has the more rapid quenching. Okay, the more severe quenching, sorry. So here the water, oil, and air are the three most common quenching media. So it is true or false? I think it's true. It's true because it is defined in this way only. The more rapid the quench, the more severe the quench. Just remember this line and then you will understand this. Okay, the more rapid the quench, the more severe the quench. So water, oil, and air are three most common quenching media. I think it's true of all. It's true. Now the heat energy is dissipated to the quenching medium at the specimen surface, and the rate of cooling for a particular quenching treatment depends on the ratio of the surface to the mass of the specimen. Is it true or false? So if we go and understand this statement in the deep, so you understand that the heat energy dissipated to the quenching medium, okay, in which we are dipping the workpiece at the specimen surface, obviously, and the rate of cooling for a particular quenching treatment depends on the ratio of surface to the mass of the specimen. So it is true. It depends on the mass. Okay. Now, tempering and aging are the kinds of heat treatment which are applied to hardened alloys. They involve certain phase transformation which make the metal structure approach the equilibrium. Okay, now this is just you can say defining tempering. The tempering and aging are the kinds of heat treatment which are applied to hardened alloys. They involve certain phase transformation, okay, which makes the metal structure approach the equilibrium. That is true. Okay, now tempering releases the stresses and reduces the brittleness. So tempering causes the transformation of martensite into less brittle structure. That is a fine polylistic structure termed as trustite. So I have told you about this trustite previously also, that one of the microstructures that we get in phase diagram study of iron carbon. Okay, and you can say that during tempering, the tempering causes the transformation of martensite into less brittle structure or less true stat. So it is true. Okay. Now salt baths. Okay, salt baths carrying liquid nitrates or nitrates plus nitrites are used for higher temperature. Okay, the salt used for these baths is generally fluorides and fluorides. So is it true or false? So I think it's true for thing. And heavy oil baths can be used for heating range from this 343 degrees centigrade to 370 degrees centigrade. So for oil heating, the bath temperature is raised to the required temperature range and then partially heated component is immersed in it. What do you call this? It is true or false? So I think it's true. It's true because in this way only the process is done. Now for hardening of steel by quenching, so the steel is cooled in oil bath. Okay, oil bath. Okay, the steel is cooled in oil bath. Conditions of dash are termed as isothermal. The related phase diagram are referred to as isothermal transformation diagram or sometimes triple T. I just told you in just few minutes ago that conditions of constant temperature are termed as isothermal. The related phase diagram are termed as isothermal transformation diagram or sometimes as time temperature transformation triple T diagrams. Okay. So we have completed our today's lecture and we have studied about another heat treatment process known as tempering and tempering baths. And you have seen that how at various temperatures also they change their you can say color of the work specimen or the workpiece, and so is the variety of this heat treatment is so you can say understanding and easy to look into. So for now, we have studied about annealing, we have studied about normalizing, we studied about hardening, and then tempering. So these heat treatment processes are used in the industries and should be known by us also as from knowledge point of view. Okay, and these are the references. Okay, you can see them, you can look into them. These references are a source of knowledge, tremendous knowledge with good diagrams. And if you find any difficulty in reading them, and so try to be you can say understand their pattern of writing or the language in which they have written. So because some authors they write in you can say you will find it difficult to read because they have some higher end English, let's say. So you can go for another book and you can read from them also, which have simple language for you to understand. Okay, you should have the capacity to understand that. So for now, these are the references you can refer them. And thank you very much for today's.